Hi everybody, today we're going to do part 2 of our curve sketching lessons. So we're going to start with f of x is 1 over x squared plus 2x plus 8. And we want to know the domain. So we're looking at the denominator x squared plus 2x plus 8, and we want to know, is this ever equal to 0? First we can see, well, we can't factor this. There aren't factors of 8, they're going to add up to 2. So we could go straight to the quadratic formula, which would say negative 2 plus or minus the square root of 2 squared minus 4, a is 1, c is 8, all over 2 times 1. And we're not going to have to go very far here, because when you look at what's under the radical, which we call the discriminant, you're going to find out we have a negative number. Let's write that a little farther. I have negative 2 plus or minus 2 squared is 4, but then 4 times 1 times 8 is 32. So I have 4 minus 32 under the radical, and that's a complex number, and we don't do complex numbers in this class. So we have to say there isn't a place where this is equal to 0, which is kind of good news because that means the domain is negative infinity to infinity. So we're thinking everything works here. Now that tells us one more thing, because remember, I don't like to do things in order necessarily. Knowing that the domain is everything says that we don't have a vertical asymptote. So let's go ahead and write that right now. Vertical asymptote, there are none. So we have two things from our list. We know our domain. We know the vertical asymptote is none. Okay. X-intercepts, also none. Every time we're looking at a rational, the only way we're going to have an x-intercept is if the numerator is equal to 0. So when you look at 1 over x squared plus 2x plus 8, and you try to make it equal to 0, that's just not going to happen because 1's not equal to 0 ever, so we're also going to say none. We do have a y-intercept. Y-intercept comes from taking f of 0. We have 1 over 0 squared plus 2 times 0 plus 8, which is just 1 over 8. I have 0, 1 over 8. We still have other types of asymptotes to talk about. So we talked about the vertical asymptote, that there wasn't one. We do have a horizontal asymptote. The power of the numerator is 0. The power of the denominator is 2. So that's bigger on the bottom. When it's bigger on the bottom, we know that we have a horizontal asymptote at 0. So there's HA y equals 0. Because we have a horizontal asymptote means we know that we do not have an oblique. So one asymptote for this whole thing. So I said usually when we're doing rationals, we are going to use the quotient rule to get the derivative, but that's only usually. This time, we can rewrite this as x squared plus 2x plus 8 to the negative 1, and then I can use the chain rule. F prime of x, I bring that negative 1 down. I have x squared plus 2x plus 8 to the negative 2. And then the derivative of x squared plus 2x plus 8 is 2x plus 2. Just to give us a better feel for it, I'm going to rewrite that as negative 1 times 2x plus 2 over x squared plus 2x plus 8 squared. So what do I want to know here? I want to know, when is this equal to 0, which again says grab the numerator. So if I take the negative 1 times 2x plus 2 and set it equal to 0, I'm just looking at the 2x plus 2 is 0. That's 2x is negative 2, which means x negative 1. Okay, so this is a critical number. We could go ahead and plug that back in really quickly just to make that a critical point. And because it's a pretty small function, I think we can just do it right here. So I have 1 over negative 1 squared is 1, 2 times negative 1, negative 2, plus 8. So 8 minus 2 is 6, plus 1, that makes 7, so I have 1 over 7. All right, so let's kind of look at what do we have so far. So far, we have a horizontal asymptote at y equals 0, so that's running right along the x-axis. I am going to make the tick marks really big. So let's say this is 1 right there, and the reason I did that is because the points we have so far are pretty small. We have a critical point that's at negative 1, 1 over 7, so we'll make that really small. And we also had an intercept at 0, 1 over 8, so that's just a little bit closer to the x-axis. We have this as a critical number, or critical point, so we could probably tell that this is going to increase until it gets there and then decrease afterwards, but there could be some concavity that we want to see, so there definitely could be some inflection points. So we need to go ahead and do the second derivative. I'm going to go ahead and distribute that negative 1, make this 2x minus 2 over x squared plus 2x plus 8 squared, just because I don't want to have to mess with that -1. I don't want to drop it somewhere. Okay. Second derivative is going to require the quotient rule. So we're going to start low, x squared plus 2x plus 8 squared. D high is -2. Then minus high, make sure you put parentheses around the -2x minus 2. D low, the 2 comes down. I have x squared plus 2x plus 8. Power 1, and then we have to remember to do the derivative, 2x plus 2, all over x squared plus 2x plus 8, now to the power 4. Okay, we've seen this before, where we have the same thing over and over. I have the x squared plus 2x plus 8. I have it on the right side. I have it in the bottom. I look at the powers 2, 1, and 4. I take out the smallest. The smallest is 1, so this completely gone. This reduces to 1 power, on the bottom now power 3. Okay, so we need to expand what's left over. So my first term, x squared plus 2x plus 8 times -2 gives me -2x squared minus 4x minus 16. I'm going to do the second part in a couple steps because I feel like it needs it. So first I see this negative and 2, I'm going to make this like a -2 and multiply -2 times -2x minus 2. So I'm going to write plus in between. -2 times -2x is positive 4x. -2 times -2 is positive 4. Keep that in parentheses because we're not done with it. We still have this 2x plus 2 at the end. So this is, be careful, you could have stuck the negative through and multiplied by 2. I just said, let's think of it as -2. I still have this bottom. Okay. So now, let's multiply out the 4x plus 4 times 2x plus 2, f double prime of x. -2x squared minus 4x minus 16 plus 4x times 2x is 8x squared. 4x times 2 is 8x. 4 times 2x is also 8x. And then 4 times 2 is 8. Okay. Lots of terms. The denominator has not changed. So let's look at gathering like terms. I have a -2x squared. I have a positive 8x squared. That gives me 6x squared. I have -4x, but then I have 8x and 8x. So 8 and 8 is 16. 16 minus 4, that's positive 12x. And then at the end, -16 plus 8 is minus 8 over x squared plus 2x plus 8 cubed. Okay. What do I want to do with this? I want to make this equal to 0. So I have 6x squared plus 12x minus 8 equals 0. And we could try to factor in and stuff, but I think it's just quicker to go ahead and do the quadratic formula. So we're going to say x is equal to -12 plus or minus the square root of 12 squared minus 4 times a is 6, b is -8, all over 2 times a, which was 6. So this, again, is the quadratic formula if you need it written down. Pay attention though, anytime you're using quadratic, make sure you're grabbing the signs to go with it. We have x is -12, plus or minus. Let's just go ahead and put this whole thing, 12 squared minus 4 times 6 times -8 in our calculator. That gives me 336 over 12. We want to see if we can reduce this radical. So I put this in my calculator. I got that 336 is 4 times 84. But then when you look at that, you think, well, I could really make that a little bit better. Let's do plus or minus. If I divide 84 by 4, I get 21. So this shows me I can take this 4 out. So what do I have? I have -12. Let's fix that. I have -12 plus or minus. The 4 came out. I have the square root of 21 over 12. So I could divide by 4. This would be 3. That would be gone. This would be 3. So now I have x is equal to -3 plus or minus the square root of 21 over 3. So what is this? These are inflection points. Let's put them in the calculator to get an idea of where they are. So if I do -3 plus the square root of 21, and I divide by 3, I get 0.5275. We're going to call it 0.53. And then if I do the same thing with -3, minus the square root of 21, and then I divide by 3, I get negative 2.53. These also need to have y values. So I took my calculator and I put in the value of negative 3 plus the square root of 21 over 3, and I got a y value of 0.11. And then same thing with the negative 3 minus the square root of 21 over 3. I got the same y value of 0.11. So we said we have at 0.53, so let's call that about here, 0.53, and we got 0.1. So you kind of need to compare what we had, and maybe it helps if I kind of rewrite the fractions for you. 1 over 7 is 0.14. 1 over 8 is 0.125, and we're looking at 0.11, so we're a little bit lower than this intercept. And the same thing over on the left side. Remember, we have the negative 2.53. So at negative 2.53, this is negative 1, negative 2, negative 3. So let's say about here. All right. So these are our inflection points. We're going to be able to answer everything now because we know our critical numbers, we have our inflection points, we have our intercepts, our asymptotes. We're going to start from the left inflection point over to the right. It goes up, right? So there's like this little arch it's making. So this little arch says concave down. So we can see concave down. And this was negative 2.53 to positive 0.53. What's going to happen when it reaches the inflection points? It has to change concavity. So down will change to up. So it's going to be up, but as it goes up, it needs to run along the asymptote. So this is concave up from 0.53 to infinity, and from negative infinity to negative 2.53. You kind of have to watch the book that you're using to see what does it want. Does it want you to give exact, or is it okay with approximate? If it wants exact, you'll have to put negative 3 plus the square root of 21 over 3, and then negative 3 minus the square root of 21 over 3. But you should be able to tell what it's asking for. Okay. These are our inflection points. So we've given our inflection points. We had one critical point. We labeled it right here, but now looking at the graph, we know that this is a local max. So we can label that to say we know the local max. We can also now tell the increasing, decreasing. So it was increasing from negative infinity until it got to the critical point at negative 1, and then it's decreasing from negative 1 to infinity. So again, we got all of the things we needed. We didn't have to do a first derivative chart test. We didn't have to do the second derivative chart test, so we didn't have to check increasing, decreasing concavity using the charts. We could do it from finding the pieces and then just thinking it through. Let's try a different type. This time I have x squared over x plus 2. So we're going to start with the domain, and we can see x plus 2 on the bottom would be equal to 0 when x is negative 2. So we want to say x cannot be negative 2. Remember, that immediately tells me my vertical asymptote is x equals negative 2. I want you to see that connection. X-intercept comes from, well, where is the numerator equal to 0? X squared would be 0 when x is 0. So I'm going to write that as a point, 0, 0, which means the y-intercept is also 0, 0. Horizontal asymptote. Degree on the top is bigger than degree on the bottom, so horizontal is none, but this time we do have an oblique. So we're going to take the x plus 2, divide it into x squared. X goes into x squared, x times x is x squared, but you need to multiply both things by x, so I also have 2x, and then you're subtracting. The x squareds cancel, but I have minus 2x that I'm going to bring down. X goes into negative 2x minus 2 times. If you want to, you can multiply through. Negative 2 times x is negative 2x. Negative 2 times 2 is minus 4. But really, you're just trying to get a line, and this is a line. So this is my oblique asymptote, is y equals x minus 2. So I wanted to make sure we did one that had an oblique. Okay, now we're ready to go on to all the calculus of it. Okay, so let's start by finding the first derivative. This is quotient rule, so I have low d high. So low was x plus 2, derivative of x squared is 2x, minus high, x squared, d low is 1, all over the bottom squared. We're going to multiply that out. 2x times x is 2x squared. 2x times 2 is 4x. I have minus x squared over x plus 2 squared. 2x squared minus x squared is x squared. I still have 4x. I have x plus 2 squared. So at least this one's coming out nice. Setting this equal to 0, I say x squared plus 4x equals 0. I take out an x, leaves me with x plus 4. So I get 0. I get negative 4. Well, 0 we've talked about already. We know this was our xy intercept at 0, 0. We can plug in negative 4 to get the y coordinate. So I have negative 4 squared over negative 4 plus 2. Every once in a while, this is easier than grabbing our calculator. Negative 4 squared is 16. Negative 4 and 2 is negative 2. This is negative 8. So I have negative 4 and negative 8. Okay. These are my critical numbers. Let's put that all together. I'm going to make a big graph. And let's say we knew 0, 0 was important, and then negative 4 with negative 8. Okay, so those were our two critical numbers. We had a vertical asymptote at x equals negative 2. And then we had an oblique asymptote that was x minus 2. So you would start at negative 2, put some in there, and then I go up 1 over 1 for the slope. Then I connect the dots. All right, this is actually enough for us to graph everything. We have this one little dot at negative 4, negative 8, but it's surrounded by two asymptotes, so we know it's got to run along the asymptote and down. Same thing happens with this point at the origin. It has to come along the asymptote and then follow the other asymptote. So you can see what's happening. This tells me that negative 4, negative 8, look at it. It went up and then down. This is a local max. 0, 0, it went down and then it went up. So 0, 0 is a local min. Go back. The function was increasing until it got to negative 4, so negative infinity to negative 4. It was increasing, and then it decreases from negative 4 until negative 2. Let's put the rest of it. It was decreasing from negative 2 to 0. So these were our decreasing intervals, and then 0 to infinity, it's increasing. Okay, so we have our max min, our increase, decrease. Let's talk about concavity. The little part at the bottom. This is concave down, so this goes negative infinity to negative 2. This is concave down. And then it'll be concave up from negative 2 to infinity. No inflection points because it didn't change at a point. Concavity changed at the asymptote, so we didn't even bother to do the second derivative here. And I want you to see this is a judgment call, right? So we're having to use some critical thinking skills to decide when do we do it, when do we not. I didn't do it because it's kind of a waste of time. I kind of look at what do I have and can I start putting the pieces together, or do I need to know a little bit more? So kind of as you get the information, put it on a graph, and that should lead you in the direction of do you need to do more. You can also check by using calculators, right, to kind of see, does it look good? Are you missing any points? We've said that you can't see everything on the graph, but it is a good affirmation that you're doing it correctly. So let's just quickly grab this function that we started with, put it on Desmos so we can just compare. So I put in x squared over x plus 2, and you can see part of it. You can see the 0, 0, you can see the concave up, you can see decrease, increase, but what's missing, I just need to zoom in a little bit more, and that happens a lot. That you may not see all of the graphs. So we want to make sure we see the whole graph, and now you can see I have both pieces. If you wanted to graph the asymptotes, you could. I can type x equals negative 2, and if you don't like that it's a straight line, I can go to the settings, and then when I click here, I can change it to a dashed line, so that way it looks like an asymptote. We also had y equals x minus 2, and again, I change the settings, I go over, and I say make it a dashed line. That way I can clearly see the two asymptotes. If you also want to really call out the max and min, you can put in 0, 0, you can put -4, -8, and then you see this really complete graph with all the points that we were talking about.